So in this problem, we're going to deal with something known as the Doppler effect. But first, let's find the wavelengths as described. The wavelength, as we know, is the speed over the frequency. So this is 340 meters per second over 300 hertz, which gives us a wavelength of 1.13 meters. This is if the siren is at rest. If the siren is in front, then the wavelength is given by the velocity of sound minus the speed of sound minus the speed of the siren over the frequency of the siren. And this is because it's getting away from the wavelength from the source. So this is 340 meters per second minus 30 meters per second over 300 hertz, which gives us 1.03 meters. So notice it's smaller than when at rest. And if it's behind, let's label this F front, lambda behind then would be V plus Vs over F. So we can get 340 meters per second plus 30 meters per second over 300 hertz, which is 1.23 meters. So your at rest wavelength has to be somewhere between the front and behind. Now for part C is where the Doppler effects comes in handy. The Doppler effect in general is given by the following equation. The frequency heard or observed by the listener is given by the ratio of the speed of sound plus or minus the speed of the listener over the speed of sound plus or minus the speed of the source times the frequency of the source, and the plus and minus will depend on whether the listener and the source are heading towards or away from each other. So for the first part, we're saying that the source is moving away from the listener. Moving away from the listener means that Vs is going to contribute a shift down in the frequency. It's going to get fainter as we go along. So in this case, F sub L for listener at rest and source moving away would be V over, because the listener is at rest so they don't have any velocity, V over B, and then because the moving away we use a plus sign for the source velocity over F sub S times F sub S, which equals 340 meters per second over 340 meters per second plus 30 meters per second. So you can see this is going to be a lower frequency times 300 hertz, which will give us 276 hertz. So it's a lower frequency because the source is moving away from the listener. Think of an ambulance coming towards you or going away from you. You'll hear it fainter as it moves away. For part D, we have a case where the siren is at rest, so S is rests the source, and the listener is moving away. So the observed frequency or listened frequency would be V. Now because the listener is moving away, that's going to also cause a downshift, which means a negative V sub L over E times F sub S. So notice there's a difference for a shift down, whether it's the source or a listener. Depends on what makes the frequency bigger or higher, depending on the case. And now plugging in, we get 340 meters per second minus 30 meters per second over 340 meters per second times 300 hertz will give us a 274 hertz frequency listened by the, or observed by the listener. And finally, for part E, the siren is moving away. So S moving away, and listener is moving towards siren. Moving toward. So keep that in mind. Since the listener is moving towards, we're going to get an upshift from the listener. And an upshift from the listener means a positive velocity for the listener. So this is going to be V plus VL over, since the siren is moving away, that's a downshift for the source, and a downshift for the source is also a positive in the denominator. And then this is going to be F sub S. So now we have 340 meters per second. The listener is moving at 15 meters per second over 340 meters per second. The source now is moving at 45 meters per second, all times 300 hertz, which will give us 277